All right, hey guys, I'm back here again, and I just filmed a video going through the example problem. So I didn't actually do number 25, that's why I'm filming it again. This video, I need to do number 25, number 33, and 35, and we'll see how it goes. So what I'm gonna do is I'm gonna erase the dimensions that are already labeled on this box, and then I'm going to attempt the problem based on the dimensions that are given me here. So we have a different box here, right? A box again I showed in the last one, like this here. Box is 3 dimensions, got 6 planes noticed on them here. Look, all these lateral faces here, it's called lateral faces here, are 4 planes on the outside, 1, 2, 3, and 4. And then we have a top and a bottom. And running in between that, we have a plane kind of that is going to contain the diagonal of the box here. I talked about that in the last video. All right, so anyways, keys to figuring out this problem is we got to figure out what the diagonal of this bottom rectangle is. We're all rectangles in this particular box, right? It's a rectangular box, or rectangular prism. We'll define that in chapter 10. So we have dimensions here of 12, so we can just start picking them out here. Let's get 12 BSR. Okay, so our depth can be 12 perhaps. Our width can be 4, let's say. And finally, our height can be 3. All right, that's how we can read it here. All right, so we'll read our 3 numbers. We'll do depth for this one. We'll do width for this one, and we'll do height for this one. Does it have to be like that? I actually don't think it does. If you look at the textbook, they might have done it a little bit differently here. But if we have the 3 dimensions of this rectangular box here we have a 3 by 4 rectangular as the front face here, a 12 by 3, right? It's going to be 3 for our whole height, right? All of those UT is going to be 3. Let's put a 3 there, okay? So maybe I'll erase this just so we can sort of get satisfied with seeing our 3 places we're going to put things. And we're going to use rectangles to help us prove the rest here. All right, so our depth is 12. So, okay, so first things first. These problems here, the 2 things you got to do. One, you got to solve for A. Our goal here is to get the length of the diagonal of the solid, okay? That is, what is D going to equal? Okay, can't do D yet because, again, well, we know that this is 3, right? So D is the hypotenuse of that right triangle that runs from, connects like maybe this corner of the box to this bottom corner of the box here. So, right, the diagonal goes across. It connects the top and bottom planes, and it connects those other 2 planes on the other side and the other 2 planes here. But anyways, this is 3. Here's A. Here's D. So we can't do this. This is the one. This is eventually, right? Pythagorean theorem. This is going to be a right triangle right here. So we're going to know that D squared is the hypotenuse of a right triangle with a height of 3 and a base of other leg, right? Other leg here of A. So it'd be 3 squared. Oops, not 3 cubed. 3 squared plus A squared. So eventually we're going to work with this equation. We can't do it yet because we don't know what A is. So let's figure out what A is here. Because this is a rectangle, it's a rectangular box, right? The bottom of this is going to be a freaking rectangle. This is 12. This is going to be 12 over here, okay? So here we have triangle TQR. Okay, watch the other video if you're getting lost on this here. I color code stuff down here, so hopefully you see it. I'm assuming you watched the other video. Triangle TQR, yeah, it's a right triangle, right? Why? It's a rectangle. Look, a rectangle has a right angle here, has a right angle here, has a right angle here, right angles going on here. So this is a right triangle with a leg of 12 and another leg of 4. And we know the sum of the squares of the legs equals the square of the hypotenuse. And the hypotenuse here is A, right? Length A. We don't know it yet. We don't know, right? Based on these dimensions, 12, 4, and 3, we can deduce, right? If we're going 4 this way, 12 this way, and height of 3, then we can deduce, right? The height doesn't matter at all. We can use 12 and 4 to get us the diagonal of the base here, which is A here. So let's go ahead. Let's do it, shall we? Let's do it, okay? So A squared. And we actually don't need to solve for A here, right? Because what we're going to do with A squared, we're going to put it in the other equation, actually. So we don't actually have to figure out necessarily exactly what A is. Let's just get A squared real quick. 12 squared is 144. Again, try to memorize your perfect squares, 1 through 15. And if you get that, 12 times 12, you know is 144. I've done it 1,000 times, so I can do it really quickly. Maybe 12 squared, you're doing that in your calculator. That's fine. Get your calculator out. Memorize it over time here. Plus 4 squared, well, that's 16. Okay, so A squared equals 160. I'm going to save you some time. Guys, if you watched the other video, like I did a little bit too much work here. I simplified my answer for A, right? In simplified radical form. Didn't need to do that? No, because over here, look at this. We got A squared. It's over here too. A squared here, A squared there. So A squared is 160. That is going to be here. So whatever this is, A is like the square root of 160. Okay, not going to worry about simplifying it here. Because when we plug it into the Pythagorean theorem, square root of 160 equals 160. Look, I can just move that 160 here. So here I got d squared equal to 3 squared plus 160. And then you're like this from one of the examples we had in class today. 3 squared is what? Is 9 plus 160. And what's 9 plus 160? 9 plus 160 is 169. And what did I tell you about 169 class today? Well, try to remember, what's 169? How can we write that? Is it a perfect square? And let's check our calculator here. Get rid of that, 169. Take the square root, 13. There we go. It is a perfect square. So D in this one, gonna be equal to 13. Okay, so just to recap how to do a problem like this, if you're looking to follow a list of rules, hopefully you get the ins and outs. That's the reason why I do the whole examples for you, is so that you can just feel it out, right? The goal is I want you to feel it out and do it pretty efficiently, okay? Things that I did to do it efficiently right here, I solved for A first using the dimensions that were given as 1 for, like, I just used the first two, and then yeah, the last two can be the height. We can do that later. What I'm saying here. Okay, so use the first two to solve for hypotenuse involving the first two. Once I had that, that becomes a leg of the other one. And then the remaining leg that's there, the remaining height that gets there, that's the other leg. Okay, and then I went and solved it using that other right triangle. Again, here are the two triangles that we have here. This is the first triangle, right? I use that over here, this one right here. And then green, that helps you use this triangle, get the hypotenuse of it. So hypotenuse is also in the green triangle up here, though, right? Right here. And then another problem down there. Get it solved, get it done, good to go. Watch the other video. If you didn't watch the other video, you might be having a lot of trouble with that. Okay? All right. Hey, this is a tricky one here. Number 33. I always get questions about this. This might be one where you present. I think I might have somebody present this one because this is a good algebra problem right here. Let's check it out. Let's pose on this question right here. Find the value of h. Oh, gosh. Guys, we can't actually use the geometric mean formulas right here. I know what you're thinking. Is this a right angle, right? Is this an altitude drawn to the hypotenuse of a right triangle? No, it's not, because we don't know if this is a right angle. We don't know if this is a freaking right triangle. We got a right triangle here. This is definitely an altitude, but no, that looks like an acute angle right here. So guys, we can't actually use one of the geometric mean formulas from section 6.1. We can't, because that starts with in a right triangle if I draw the altitude of the hypotenuse here. This is just an altitude to the side of a triangle. Again, it's not a hypotenuse because we don't know if that's true, right? We don't know that. It doesn't look like it's true. It looks like this large angle here, PYR, right? PYR, if it's Y right here, looks like an acute angle. It looks like an acute triangle. So we got to get H some other way. So my guess is here we're going to use Pythagorean theorem, because this is the Pythagorean theorem section. You just got to ask yourself, what section am I in? And I'm probably going to use those methods first and foremost. So this is probably a Pythagorean theorem problem. So what can I set up in terms of Pythagorean theorem to solve this one? Well, let's check it out here. They're giving me hints. They say, let PQ equal X. So here we got X right here. And here we got 21 minus X. Where did that come from? All right, there's 21 minus X. Kind of hard to see. Where did that come from? Well, the whole third side of this triangle is 21. Right, it's 21. So if I'm going to create an algebraic expression for this, I'm going to let this, represent a particular length, because as we know from the ruler postulate, any segment has a particular length that could be expressed by as a real number. So X is a real number, got to be less than 21 somehow. This is going to be 21 minus whatever X is. This little segment here is dependent on how long that is right here. So I can just make that 21 minus whatever this is here. And those are two expressions that just involve one variable, just involve X here. All right, so what we're going to do here is we're going to set up two equations using Pythagorean theorem. Check it out here. 20 is the hypotenuse of this right triangle here that's on the left of our diagram. So I know that this statement is true. 20 squared equals h squared plus x squared. Next part of this that I know is also true is this. 13 squared equals, well, I got this action right here. I got 21 minus x, right, which they said let it be that one, squared, plus h squared, plus h squared. Okay, look at this here. Oh gosh, how are we going to solve this? They recommended this. I'm just like, I'm trying to, right? A lot of these geometry, you just try different approaches, right? Try different approaches. The only risk is not taking any risk at all and not trying to sketch it out, not to put some ideas down. So I have this, and do I panic? No. I think, what do I notice? I'm going to peek at it. I see a few things here. Okay, well, let's just take an inventory. Take an inventory of what's going on here. Look, see what you have. Look, see what you can work with. This is what it's all about. Math, you get stuck all the time, but you do the practice getting unstuck, not just like a question mark, too hard. Not too hard. Let's get it. Let's get it. You can get it too. Okay. So check it out here. I got two variables. So I'm not going to be able to solve for h. I'm not going to be able to solve for x. I'm trying to find h. That's ultimately my goal. I can't do it. What I can do is this. Check this one out. I might be like, well, how am I going to get h? Well, I'm going to take x squared away from both sides of this equation, right? Because remember, if I take one thing away from one side of the equation and I take away from the other side of the equation, then my equation becomes balanced, right? It remains balanced. Okay. This is 20 squared here. That's 400. Okay. I try to follow along with me. It's kind of hard, ugly writing here. That equals h squared. Okay, I got that. I could try to take the square roots of both sides. That's kind of useless here. Wait a second. This is a system, isn't it? Look, I have an equation here that I know is true based on this left-right triangle. I have an equation over here that I know is true based on this right triangle. I just got to solve the system, right? So I have here h squared isolated. I know h squared equals negative x squared plus 400 because I just isolated it over here. What if I isolate x over here? Sorry, h squared over here. If I isolate h squared over here, let's do that here. So I'll do 13 squared, and that's 169, minus, okay, here we have 21 minus x squared. I might just like expand that because that's kind of confusing right here. I want to take away this from both sides, okay? But what this equals here, right? You gotta, it's a common mistake that people make here. This isn't 21 squared minus x squared, it's this, right? Remember, this is a square, right? What's the width of the square? Well, it's 21 minus x. What's the height of this square? Well, it's 21 minus x, right? Minus x. I don't know if you guys do generic rectangles or you do foiling in your Algebra 1 class. Remember foiling here? All right, well, 21 times 21 is, well, that's a little hard. Like, what do we got here? 20 times 20 is 400. Add 21 to it, would be 421. Add another 21. Oh, my eyes here. Wait, add another 20. So I think it's 441. I think that's what it is here. Let's just double check it here. So 21 times 21 equals 441. Okay, so this is 441, right, which is 21 squared. But check it out here. Minus 21x, right? 21 minus 21x. Okay, negative x times negative x, well, that's just positive x squared because a negative times a negative is a positive. So here, right, what I'm taking away over here, let me just expand it here. So we'll have to do it for later. I'm taking away x squared because I'm taking away that. Here, this is negative 42x here. I got to add that to both sides to get rid of the negative 42x. Probably showing too much work, not showing enough work on this one here. It's getting more confusing than it needs to be. Okay, this here, we'd have this here, this 21 squared would represent positive 441. So I want to take away from both sides. Okay. I might have lost you here. You might have come meet with me on this one if you want to get this one here. But basically what I did here is I expanded this, right? This here, right? The inside here, this is the product is 21 minus x squared. The sum, way I write this polynomial as a sum is I squared. I get 441 minus 42x plus x squared, right? That's one way I could rewrite this, right? If I squared it, it becomes this, right? That minus 42x is just twice times negative 21x. What I get when I multiply 21 times negative x. And I have to do that twice. Anyways, this would be on this side of this equation. That's why we have all the negatives over here, right? Instead of positive x squared, I subtracted x squared from both sides to get rid of that. Subtracted 441 here to get rid of that. And I added 42x to get rid of that. Okay, you with me here? You with me here? All right, check it out. Why is that important now? Check it out. I have h squared isolated. Oh, interesting. So h squared, it equals that. H squared also equals that. So what can I do? When two things, h squared and h squared, each equal the same thing, then those same things, they do what? They equal each other, okay? So in Algebra 1, we call this the equal values method of solving an equation. And what you've been seeing in geometry is we would call this transitivity. One thing equals another thing, and that same thing equals yet another thing. Those two other things must equal to each other, right? Because they both equal the same thing. Two things each equal the same thing, equal each other, okay? Negative x squared is here, plus 400, right? That was just that 20 squared originally. Man, 20 squared is so much easier. That equals 169 minus x squared plus 42x minus 441. So we need to start combining like terms and solving for x. Man, this is actually a really hard problem. Dang. Okay, this is definitely a challenge here. All right, so we got the x squareds here. So what I can do is I can add x squared. This makes it a little bit easier. I can add x squared to both sides. Those cancel out. Okay, I got 400 over here. So let's just keep. I want to combine those like terms. Let's see, 4x is here. So I got positive 4x over here. So I'm going to move everything else to the left side. Take away 169 here. I got to take away 169 over here. That goes away. That goes away. I got to add 441 over here to get rid of that. Got to add 441 over here to make sure we keep the equation balanced. Okay, and then I have 4x isolated here. Okay, 400 plus 441 is 841 minus 169. Whoa, I definitely got to use a calculator. So let's check it out. 441 plus 400. You with me? You follow me? This is a lot. Minus 169. And, 672. That looks nice. 4 is going to go into that nicely. So here, I got to bring down my 4x. Okay, and that's equal to 672. And exact 4 goes into 672. So we can just divide this by 4, and we get 168. Okay, so I got 168 for x. That doesn't make any sense. I made a mistake at some point. Where's my mistake? How could x be 168? It can't be 168. Where's my mistake? Oh, geez. Oh, it's 42x. Yes. I rewrote this wrong. It was plus 42x. So anyways, yeah. I got to bring that one down, okay? So I made a mistake there. All right, maybe you got it. Remember, it was 42x when I did this stuff here. Oh, connects, man. It's just a challenge problem for you guys, looking for a challenge here. Making mistakes, going through the fine-tooth comb. Is that a thing? I don't know. Yeah, I guess that's a thing, huh? 672 divided by 42. And it equals 16. That makes a lot more sense. There we go, 16. Boom, x is 16. And now we can double check our answer to see if we got it right. Okay, if x is 16, that means 21 minus x is going to be 5. And check it out. This is a Pythagorean triple. Yes, 12. 12 is my h, right? Because 5 squared is 25. 13 squared is 169. 169 minus 25 is 144. Square root of 144 is 12. Okay? 12, 16, 20 is in a 3 to 4 to 5 ratio. And 3, 4, 5 is a Pythagorean triple. I know I got the right answer. I double-checked it. 16 equals x. Wow. That was tough. What was the point of me asking you a problem that hard? I don't know. I mean, it's just like it's looking through and trying different things and clawing and fighting your way. And perhaps you can explain this one. Or number 34 next class, right? Because you got to the top of the mountain. All right, check this one out here. This one might be hard to see in your problem set. This one says here, not 0, O. O is the center of square ABCD. So that's where the point of intersection of the diagonals. So maybe let's sketch it out here. That base of the pyramid, of the square pyramid, okay? So we'll define what a pyramid is a little bit later in the textbook. We don't need to worry about it now. We're not deducing anything really about it that requires knowing what a square pyramid is. But it's a square at the bottom, okay? We got square ABCD. Okay, so where point O is going to be, well, this is one diagonal. This is another diagonal. Boom, boom. Okay, and we got O right here. Okay, so O, this is our center of the square, right? That's the center, okay? Point of intersection of the diagonals. Okay, VO is perpendicular to the plane of the square. Okay, VO, so yeah, so this is we got something shooting down here. This is perpendicular. So that's going to involve a right triangle. So know what you're thinking, Pythagorean theorem. Going to do it at some point. So we know that that's right. We also know that VO, well, here, this is a little bit hard to see, but it says here that maybe you'll have trouble seeing this in the book, especially if you don't have a physical book here. You're just looking at it online. It says here, VO is the perpendicular to the plane of the square. OE, find OE, the distance from O to the plane VBC. So here we have this side triangle right here. Okay, we have this side triangle. This is triangle VBC, and OE is the distance to that plane. Okay, what do we know about distances? Well, we know that distances it would be the length of the segment that's perpendicular from that point to the plane. That's the definition of a distance from a point to a plane is the length of the perpendicular. The one and only perpendicular you can draw from a point to that plane. So here we know that OE is perpendicular to the plane, right? Plane VBC, the one that contains this triangle right here. So find OE. We got to find that. Ooh, this is a tricky problem here. Find OE. Distance from point O to the plane VBC. So we have a right triangle. We have a bunch of right triangles to deal with here. Which are the ones that are going to help us? This is 30 right here. Okay, this is 30 right here. So the whole thing's 30. This is another thing worth pointing out here as you're dealing with this puzzle. This whole thing is 30. Okay, so what can help us? I don't know. I'm freaking out a little bit here. Freaking out. Well, what about this? They give us you that this is 20. Again, this is a right angle here, right? I'm gonna put the right angle there so you can kind of see it. All right, that's a right angle right there. This would be a right angle over here. Well, then, how about this? You ask this here. Can you prove that that's 15? Okay, is that 15? That's this in this diagram here. Can you prove that this is 15? And the answer is yes. You can totally prove that. And that's 15 right here. How could you prove that? Well, this would just be right perpendicular to this side here. So this would be, let's see, the diagonals of a square bisect each other because they're a parallelogram. So this is congruent to that. And right, let's just introduce that perpendicular. That's what that thing is right here. Okay. So this would be HL, right? Through HL, this triangle is congruent to that triangle. And right, that could be repeated around. You could repeat that. So HL. So these are all congruent triangles. So this has got to be 15 here. That triangle's over there 15. So this is going to be 15 there because CBCDC. Anyways, you can prove that that's got to be half of this 30 length here. So that's 15 right there. Okay, so that's going to buy us this triangle here where VO is one of the sides, and then we have O, and then let's make this one point Z right here. And then this is length of 15. This is 30. We can get that what is called what is this called? The height, not the height. What is this called? This is called the slant height in chapter 10. This is the slant height right here. VZ might be useful to us to solve for potentially. Or is it? I don't know. They don't give us that point there. But I got a right triangle. That kind of helps. Well, anyways, can we do like geometric mean stuff? Well, there's a few ways we can actually do this. This is actually kind of an interesting problem to think about here. So I'm not even to bother with Z right here. I'm not going to bother this whole thing here. I'm going to do this here because we can actually get this. Ooh, this is a good problem. I like this problem. I can get this. Ultimately, this is what we're trying to solve for here. That's why you're sketching it out and picking and clawing your way to see if you can get this. What we're trying to get is this, right? The length to this plane, VBC, right? VBC. So that's going to be the altitude of this triangle, VOC. Ooh, what do we know about altitudes? Okay, so this is going to be our X. This is going to be our goal to get this one. Well, our altitude here is going to be the geometric mean of the whole hypotenuse. So let's get that. Let's maybe get the whole hypotenuse. Let's get VZ. I think we're going to get VZ right here. So VZ squared is going to equal 15 squared plus 30 squared. Okay, and then VZ, because I'm using Pythagorean theorem, right? There's Pythagorean theorem. 15 squared is 225. Again, it's helpful to memorize. Perfect square is equal to 15. 30 times 30, you can just do that in your head, right? 3 times 3 is 9, and then you have 2 zeros on top of that, right? So this would be plus 900. That's VZ squared. So VZ squared is going to equal 675. Perfect square that goes into it is definitely 25. We'll go into that. So we'll definitely use that when we sort of simplify this. So VZ equals square root of 25 times what? So 675 divided by 25. 27. Ooh, 9 is going to go into that again. So times by 9 times by 3. Okay, so we're going to bring out a 5. So 5 times 3, 15. So we get 15 root 3. So VZ is 15 root 3. This is how we're going to do it. And then, guys, we spent that last class. This is a good problem. I like this problem. 15 root 3. There might be an easier way to do this. I might have this on Wednesday's thing. Like, present this one out if you got it. This is 15 root 3. Okay, there's your 15 right there. Okay, there's your X. That's your altitude here. So you know what? I'm going to use that geometric mean action to figure out what this is. All right, I can get this one here. I'm going to make this one. Let's let this one be Y. Y here isn't the geometric mean, but here, look at this here. 15 is the geometric mean between Y and 15 root 3, right? Here, this is a leg of a right triangle. Man, a lot going on. This is the way I'm doing it. I don't think I'd solved this one before like this, but I'm going to keep flowing. This is 15. It's a leg of a right triangle. Here's the altitude drawn to the hypotenuse. So the altitude drawn to the hypotenuse, this leg is length. It's going to be the geometric mean between the whole hypotenuse and the segment of the hypotenuse that's adjacent to that leg right here. So I can write this. I know that this is a true, if I've done everything correctly, I know that this is a true statement. 15 is the geometric mean between y, which is what I made this segment of the hypotenuse, and 15 root 3. Okay, to get this one cross multiply, I get 225 equals 15y root 3. Okay, divide both sides by 15. I get 15 equals y root 3. Divide both sides by root 3. I get 15 over root 3. My denominator is not rationalized. It's not a rational number. So I need to multiply this by root 3 over root 3. Okay, and I end up with y equaling 15 root 3 over 3, which equals 5 root 3. Okay, so what I know now is that this is 5 root 3 right here, okay? These are 15 root 3s. I'm going to know that this is 10 root 3. Whoa, I got that really quickly. Why? Well, the whole hypotenuse is 15 root 3s. That's how many we have. 15 times about 1.7. This is 5 times about 1.7, or 5 root 3s. So the difference between 15 root 3 and 5 root 3 is 10 root 3, right? If I have 15 root 3s, I take away 5 root 3s away. Summation postulate means this plus that equals that. Well, this is going to be 10 root 3s. Okay, so x is the geometric, man, this is the way that I solved it. Maybe you got it a different way, but I'm also explaining it too at the same time. That's the reason why it's taking so long. X here, so here, all right, I think x is the geo mean between 10 root 3 and 5 root 3. Okay, so we can actually solve for it because this is our altitude. And these are the two segments of the hypotenuse. We know that the altitude of a right triangle to the hypotenuse is the geometric mean between the two segments of the hypotenuse that altitude creates. And let's go ahead and solve for it right now. X is the geometric mean between 5 root 3 and 10 root 3. X squared equals 50 times by 3, right? Because root 3 times root 3 is 3. 5 times 10 is 50, equals 150. Let's bring this over here. X squared equals 150, so that means square root of x squared equals square root of 150. We can totally simplify that one because 25 goes into 150 6 times, right? 6 times. So, hey, you know what? X is going to equal 5, right? Because square root of 25 is 5. I can factor that out and then be left with 25 times 6, right? It goes to 150. So I end up with 5 root 6. And I'm hoping I got that one right. I'm hoping that OE equals 5 root 6. And let's see. Let's see if we get the big payoff, or I'm going to have to film another video. Because I will. I do it. It's 12. What did I do wrong? Sometimes I do it wrong because I'm spending too much time explaining. I did it wrong. All right. What did I do wrong here? Okay. Well, that's 15. That's 30. It's Forden. Let's see here. Did I do this wrong here? Oh, I feel like I made a mistake over here. Let's see. 225. Okay, it's 15. Is it rationalizing? No. The answer is 12. But how? Why? I want to film another video of this.